Hello, and welcome to A Bit of Tech, a Nokia Bell Labs podcast celebrating our centennial. I'm Aron Heller, and I'll be taking you on a journey through where we've been, where we are, and where we are going. Bit by bit, we are going to unpack the past 100 years and explore the next. Nokia Bell Labs scientists have made groundbreaking discoveries and innovations that have spawned the digital age and revolutionized our world. It's impossible to overstate just what an impact we have had. Simply put, without Bell Labs, modern life as we know it would not exist. We've established the foundations for modern communications, computing, and the internet. But we haven't just set the standard for the telecom industry. We've defined technological trends. Wherever we go, wherever we are, we all carry a bit of Bell Labs history in our pockets. Bell Labs scientists have made groundbreaking discoveries and innovations in radio astronomy, cellular communications, and information theory. Our own Claude Shannon was the first to use the term bit, those binary zeros and ones that make up the digital world. We didn't stop there. Here's just a few of our other transformative inventions: the transistor, the laser, the solar cell, the Telstar satellite that enabled live television broadcasting, the charge-coupled device that enabled digital cameras, C language, the Unix computer operating system, and there are so much more. Today, this legacy lives on as we continue to penetrate every corner of human existence and chart new paths and technologies that address humanity's most pressing challenges. And our innovators are hard at work on the next big thing, turning the world of the future into reality. We're going to dive into all of this in our podcast series, devoting individual episodes to our groundbreaking work in these foundational technologies and in areas as diverse as artificial intelligence, quantum, sensing, and the space economy. Each episode will focus on a different aspect with a different guest. But in our very first episode of A Bit of Tech, let's kick off with an overall look at perhaps the most influential scientific institution of the 20th century. And I can think of no better place to start than with the presidents of Nokia Bell Labs, Peter Vetter and Thierry Klein.
Thank you, Aron.
Thanks for being here. Peter, you had the Nokia Bell Labs core research, and Thierry, you had the solutions research. Could you give us a brief introduction on each of you and each of your domains?
So core research, as the name says, it addresses the core business of the company, the longevity of the portfolio in mobile networks, optical networks, network systems, and security. And then also the foundational technologies for the enabling devices like optical and silicon photonics, or also ASICs.
Aron, and Bell Labs Solutions Research, our mission is to look at new technologies, new markets, new customer segments, new business models that would expand the portfolio of Nokia into new domains. So when you talk about new technologies, of course, it's AI, but also blockchain, Web3, new device technologies. New markets, new customer segments would be going beyond the service provider market into enterprise, industrial applications, space, defense, and so forth. And new business models is about how do we create value out of the research, transferring the research to the Nokia business units, but also looking at other avenues for value creation through partnerships, JVs, licensing, and spin out of technology.
Well, it's great to have both of you here, and thanks for joining us. It's great for the first episode to start off with you guys. So let's dive into it. Let's get started with a bit of history. It's been 100 years since Frank Jewett became the first president of Bell Labs, and you two are now respectively the 14th and 15th. So looking back today, what do each of you consider to be Bell Labs' greatest contribution, its greatest legacy, I guess? Peter, why don't we start with you?
Yes, since you mentioned Frank Jewett, let's even go before Bell Labs started. The AT&T realized if they want to realize market leadership, and they had this vision of having a nationwide network that you can make a phone call coast to coast. That was not possible in the day. They needed foundational research to make it happen, and they started that research in 1907. And Frank Jewett was on that project, and they looked not into better relays or better magnets, which was the state of the art at the day. They embraced a new technology, vacuum tubes for amplifiers. And they analyzed how does that thing actually work and how can we come with a better configuration. So foundational research. And then indeed in 1915, they achieved this coast-to-coast communication, the first communication. And the realization you need in-house long-term research to maintain that technology leadership and help humanity. And it is this thinking of what is the hard real-world problem, go after it in a disruptive, think out of the box way, and grounded in the fundamentals of science. And in this way, we've continuously set new trends. I mean, the other one that I would highlight is a nationwide wireless network. Again, the same big problem. How do you do that? Frequency reuse, the invention of cellular networks. And maybe a last one, transcontinental, across the Atlantic, this idea of putting a relay in the sky that led to the very first Telstar satellite, the communication satellite in 1962.
What about you, Thierry? Are there any previous presidents that you look back for with inspiration?
Well, he wasn't the president of Bell Labs, but one of my heroes is Claude Shannon. My degree was in information theory, communication technology. So Shannon is really the father figure of information technologies in the digital information age. He wrote a very seminal paper in 1948 with a mathematical theory of communication and really established how much we can communicate, how much information can we send over a communication channel, whether it's wireless, optical, whatever the channel may be. And it really set us on the path to understand how much information we can send, and then led to a lot of research afterwards on achieving that limit. And the Shannon limit is probably one of the foundational theorems in communication information technology. Interestingly, he also did early work on artificial intelligence. And he particularly worked on a project with a magnetic mouse that learned how to find its way in a labyrinth, and then remembered. And when you changed the setup of the labyrinth, it would relearn how to find its way through it. So he's just been a very influential figure in a lot of domains, and really not just the research he did, the content itself, but also how he thought about problems. And how he took very complex problem and had a way of distilling it to the core and the essential questions that needed to be answered, has really been a profound impact on myself, a lot of people at Bell Labs, and a lot of people in information and technology at large.
You got ahead of me there. I was going to get to Claude Shannon. There's so many things, so many highlights. You think about information theory, that was a big one, but you've also got the transistor, Telstar, Unix, so many of these amazing discoveries and inventions. I personally love the story about how a pair of Bell Labs researchers who were working on something completely different, and then they accidentally stumbled upon proving the Big Bang Theory and the origins of the universe. That was just one of my favorite stories. Do either of you have a personal favorite, something that jumps out at you as something that really highlights what makes Bell Labs so special and how it's influenced the world?
I think the one you mentioned, when Arno Penzias and Bob Wilson did research on radio astronomy, and they discovered really the first experimental proof of the Big Bang by seeing this noise signal in their measurements, and they didn't dismiss it. They stayed curious. They investigated to understand what it was. They tried to eliminate all kinds of potential sources for it in their experiments, but they couldn't. And but they didn't dismiss it, and they talked to people at Princeton University, and they realized that what they were measuring was the background radiation from the Big Bang. And it's one of the favorites, I think, for myself, for Peter, for everybody, because it shows a part of Bell Labs DNA, that we work on the hard problems, but we always keep our eyes and ears open for what may be left and right, what maybe we stumble on, and we're not quite sure what it is, but we don't dismiss it. We then explore in that direction further, because we want to really understand what the experiment shows, what ideas come up as part of doing the main research. But there are so many other discoveries that you might make accidentally. And in this case, the side path turned out to be much, much bigger and much, much more important than the initial experiment that they worked on. And that's always possible. And I think everybody remains curious to say that you're working on something, but there may be something on the side that ends up being a much bigger discovery.
Yeah, I remember talking to Bob Wilson about that once. In the beginning, they thought that it was pigeon droppings for a while that was making the noise. And then they had to eliminate all these things. Eventually, they found out the Big Bang Theory. What about you, Peter?
Well, there's another similar story. For instance, our most recent Nobel Prize winner, Louis Bruce, who got the Nobel Prize for quantum dots. He was initially working on a project to improve solar cells and the idea that maybe photochemistry could be used to that. And he came across nanocrystals. And he discovered that the color of the light that these nanocrystals emit depend on the size of the nanocrystal. And he digged in and tried to understand what that is, and he started then using the quantum mechanics to really explain it. So again, this curiosity, not dismissing an observation, but trying to fully understand it, and then later on, we started using it, and in present day, we have quantum dot LEDs now.
Well, you mentioned the awards there about the Nobel, the recent one. There have been so many of these prizes, hundreds of them from so many different organizations. 10 Nobel prizes, 5 Turing awards, U.S. medals, even 3 Emmys, 2 Grammys, and an Academy Award. So you got for the entire gamut over there. Anyone has especially influenced you guys, Peter?
Given that most of my career I have done research in optical communications, I'd call out Charlot and Townes, because they invented the laser that has really been transformational for optical communications. They didn't get the Nobel Prize for the laser. They got later in their career Nobel Prize for other work which they did at university. But I still want to call those people out because that invention of the laser was so transformative for the future of optical communication. But since you mentioned Turing Award, last week I actually met Jan LeCun, who invented the neural networks. And again, it started with a real problem. AT&T wanted to read handwritten phone numbers, and he came up with this solution for image recognition, neural networks, that is now so foundational for present-day AI.
So, Aron, I'm going to go maybe against what you expected to say on which one is our favorite award. I will say none of them, really, because the point is not that we're going after these awards. The point is that we do research on disruptive technologies. We do research to solve the hard problems of our generation. Those problems change from one generation to the other, of course, but the point is always to solve the hardest problem of that generation and that decade. And solving the hard problems, coming up with solutions that have an impact on humanity, society, industry. And if you solve the hard problems and you come up with solutions that have that demonstrable impact, you will be recognized. You will get these awards. I look at the awards as a collection, as a totality, that we have done a lot of really great and impactful work that had a profound impact on all of us, on how we live, work, communicate with each other for decades. So it's not one award, it's just a testimony to the DNA of Bell Labs research, that we solve the hard problems, we have an impact, and then the recognition follows from that, but it's not a goal in itself. The Nobel Prize is not a goal in itself. The goal is to solve the hard problem, have an impact, and change the world around us.
Well, obviously, we're focusing a lot on the legacy now because we're recognizing the centennial, the 100 years of Bell Labs. But and there's so many of these stories that are on our website too, so viewers can check out over there to learn more about it. But I want to fast forward a little bit for you to today, because we talk about this legacy and it's amazing. But in your current roles today and in the projects that you're working on, how do you see this legacy playing out in present day and in our lives now?
An important challenge that we see for future networks is so the AI is absolutely the talk of the day, right, in the revolution that it brings. But the network is really central to that and enabling that future of AI. It's collecting the data from a massive scale of sensors, bringing it to the data analytics and compute capabilities in the cloud, and then bringing outcomes back to humans or robots and machines. So, and what we're seeing is, on one hand, that we want to enable this future in a network cloud continuum, really like an integrated platform to enable and expose these capabilities to application developers and users. But then we also see how the capacity demand goes up in the access network, the wireless access network. In the coming decade, we see that capacity will go up by a factor of 10. It's actually been so for several decades already, and that will continue. In the transport network, intra and inter data center, in parts of that network, it doubles almost every year. So that means over a decade, a factor of 100. That's nothing to sneeze at. You need really disruptive innovation to keep up with that capacity demand. And at the same time, the power consumption cannot go up by a factor 10, factor of 100. The cost cannot go up by a factor 10 or 100. So you need really innovative, disruptive solutions to keep up with that trend. And so there's what networks can do for AI, but then also there's what AI can do for the network.
Thierry, how about you? The Nokia Bell Labs legacy in present terms.
Yeah, I would just follow up on what Peter said about AI for networks. We talked earlier that AI did not start with ChatGPT. AI started way back. Shannon worked on it. Jan LeCun worked on it. And so there's a lot of research that we're doing today on AI, the foundations of AI, the mathematical models, the tools, the methodologies, and really the underlying machinery of AI and machine learning, independently of what the application and use case is. And then to augment what Peter said, then we're looking at AI for networking, and we see AI really coming into all networking technologies, whether it's wireless, broadband access, IP, optical. It doesn't really matter. All network domains will benefit from AI. And we see AI coming in throughout the entire life cycle of a network, whether it's the design of the network, how to bring AI more into the network to make them AI native from the ground up, how to bring AI into the deployment of the network. For example, where should we deploy wireless base stations? How many? Which configurations? So in the deployment phase, then in the operational phase, how do we optimize the network while it's deployed? For example, as traffic demand changes between rush hour and nighttime, traffic patterns change, the amount of traffic on the network changes. How do you adapt your network to handle the traffic demand, but at the same time minimize your energy consumption? So that's one very good example where AI will come in. And then we also see it coming into the customer care, maintenance, troubleshooting, predictive maintenance, just to make sure that the network stays up and reliable. So multiple facets during the life cycle of the network. We also see lots of opportunities for AI in the enterprise and industrial sectors. The fourth industrial revolution going into the fifth industrial revolution will start with connectivity. It'll start with compute platforms and cloud computing, but it also needs a lot of AI to solve these business challenges around productivity, efficiency, safety. And so we're expanding the research into AI-driven technologies for understanding physical worlds and making better decisions for these business problems in enterprise and industry.
Well, obviously, AI is the hot topic now. Everybody's talking about that, and Nokia Bell Labs has got such an amazing legacy with that, going back to the days of Claude Shannon. As I mentioned, we're going to have individual deep dives in our podcast series here. AI is going to be one of them, but we've got 5 key areas of innovation that we're focusing on. We're going to have a specific episode for each one of them. We went over AI, but maybe we can get a little bit of a sneak peek of the other ones as well, just sort of briefly. Thierry, let's start with you about space, the final frontier. Bell Labs also has a really long legacy there as well. You mentioned Telstar and the Big Bang Theory, but we were also involved in all the previous NASA missions and developing the lunar economy. We have an upcoming NASA mission to the moon as well. Can you tell us a little bit about our space portfolio?
When we think about the next 10, 15, 20 years and the vision and the ambition of more sustained human presence on the moon, eventually on Mars, deep space exploration, all of those missions, whether they're commercial or government missions, they all require advanced communication. It's not just two astronauts talking to each other and voice. We need high data throughput, low latency, high reliability, because we want to have these data, video, robotic applications in all the future missions. So we need absolutely advanced communication networks. And then the question is, why would you not want to use the technologies that we deploy every day on Earth, that we deploy with service providers, that we deploy with enterprise, that you and I use every day? We have so much technology in our pocket. Why not take those same technologies and bring them to bear on these future requirements of missions in space? And that's really what we set out to do. Leverage everything that we have done in terrestrial networks, take those technologies into space, starting with the moon, going deeper into space afterwards. And then, of course, adapting the technologies to make them suitable for the harsh environment and the particular operational requirements of the mission. But at the core, it should be built on the same foundational technologies that we've developed and deployed for decades.
Peter, I want to jump over to you on sensing. That's another one of our big themes. We're going to have an episode on that as well. I grew up learning that there were 5 senses, but you say there's a 6th one, right? A digital sense. What's that about?
So we call it the network with a 6th sense, and that sounds a bit esoteric. But when we say a person with a 6th sense, what does that really mean? That's a person that picks up very small signals, feeds that to her neural network, the brain, and subconsciously develops a foresight and an insight, and say, "Oh, this person has a 6th sense." Now, imagine we augment human capabilities, connect the massive scale of sensors, augment the neural network with the AI capabilities, and then get a better understanding of what is happening in the physical world, what is happening with humans, and use that to then predict and plan better outcomes. So network with a 6th sense, and you can apply that in smart factories, in smart cities, in agriculture, even in healthcare. And it's not only connecting sensors, actually the network itself can also be a sensor. The radio base stations that will be ubiquitously around us, we can use these same radio signals also as a radar. And we've shown, as a world first, that it can be done with 3GPP small cells without impairing the quality of service of the communication. And then you can start using that in smart cities to see the flow of traffic, anomalies, flow of people, or detect drones. Benign drones, are they behaving according to flight corridors, or malicious drones maybe, and that shouldn't be there. And it's not only the radio base stations, actually also fibers and we have a large mesh of fibers on terrestrial networks, but also submarine. They can also see small mechanical changes, like in submarine waves or seismic movements, and use that to understand and predict earthquakes or ocean currents. So yeah, the network with the 6th sense.
That's pretty amazing. I've spoken to a couple people, and just the environmental impact it can have as well seems like it has a big influence.
We touched a little bit on the 4th or 5th industrial revolution and what Peter said about sensing. The sensing is such a foundational capability at large to build up an understanding of the physical world. And when we talk about ourselves as people, we talk about spaces, we talk about industrial enterprise environments. If you want to optimize that and you want to get better understanding, it starts with sensing and collecting information on what's going on around you. What does the world look like around you? If you want to optimize process flow in a factory, you want to optimize a supply chain, you want to optimize an energy grid, it starts with collecting information. And so sensing is really important to collect that information in multiple different ways, multi-level information and data that you're collecting, because without that, you can't optimize. And then AI will, of course, come in to extract useful knowledge and insights from the data that you're collecting. And that allows you to then make intelligent decisions that improve your process, improve your healthcare, improves your well-being, improves your industrial processes, whatever you might want to apply it. But that sensing coupled with AI-driven understanding is really core to optimizing the world around us.
So we've covered the space, AI, sensing. Another area that we're at an inflection point in, we're very influential in, is quantum. Peter, I thought I heard you say at some point that a quantum computer could be the next transistor. What did you mean by that?
Absolutely. So we're working on a unique concept in quantum computing. And maybe I should take a step back, because the transistor is really a manifestation of insights created in the early part of the previous century on quantum physics. People like Niels Bohr, Schrödinger, Heisenberg. And that enabled a revolution of inventions, the transistor being one, solar cells, semiconductor lasers, that built on that knowledge of quantum. But we call that quantum 1.0 because we treat the particles still as an ensemble. A sea of electrons in a laser, for instance, in a semiconductor, or a stream of photons. Now we are indeed at an inflection point where we are able to manipulate individual particles and use them to our benefit for quantum computing, but also for quantum networking. And at a level of quantum computing, we work on a fairly unique qubit concept. There's several research groups around the world that work on qubit concept, but the one that we are pursuing is a topological qubit that has the promise of being very scalable, meaning you can create a computer with millions of qubits that you would need to do these complex future problems that get exponentially hard when you do them with a classical computer, and that you really reach that quantum supremacy. Think DNA sequencing, think design of proteins and medicines, things of new materials for batteries, things of complex delivery planning of multiple drones in a warehouse or so. So with our topological qubit, we are onto a quantum computer that really can deliver to that promise. On the quantum networking, there it is really enabling the entanglements, spooky action at a distance. And one of the applications is actually detecting intruders, because if between A and B we see an eavesdropper that tries to pick the information, the endpoints will see it because you break the entanglement. So this is used for a concept called quantum key distribution. Today, this is only possible on a single link. So a future research direction is, can we do quantum networking where you maintain that quantum entanglement across a network and enable quantum key distribution across a network? And then possibly later on even do distributed quantum computing.
Well, it's really interesting that all these elements here, the AI, the quantum, all the others, they have at Bell Labs sort of a past, present, and a future component that we think that quantum is this brand new thing, but it's been in our legacy there. And probably that brings me to the last theme I wanted to touch on here, which is foundational technologies. And that's sort of like the bread and butter over here with, the Gs and with MIMO and optical. Could you guys talk a little bit about that, about our legacy there and how we're still influential in that regard today?
The foundational technologies are really core, whether it's on the fundamental mathematical understanding. We talked about information theory, the fundamental understanding that leads to new materials, new devices, whether it's then applied to optical technology, wireless, or computing, like with quantum computers. I think for us, it comes back to understanding what are the hard problems that you try to solve, and we're not trying to solve them in with an incremental improvement of 10%, but really looking at what are the trends, where is the current technology trend not sustainable, whether it's from an energy perspective, from a fundamental limit perspective, from an operational perspective, or even from a business perspective. What are some of the trends, and where do we need inflection points in the technology path? And that's when you're really solving a key problem, not just solving something that makes it 10% better. And a lot of that has to be grounded in a scientific understanding of the core technologies. And you need to really have that understanding. Otherwise, you don't see the other options that you would go. You would just try and make it better. And Peter talked about the transistor at the beginning. When we invented the transistor, it was replacing the vacuum tube. The research was not to build a better vacuum tube. The vacuum tube was known to be not energy efficient, not reliable, and too large. But the research was not to build a more reliable, smaller, more efficient vacuum tube. It was really saying, this is not going to be sustainable. We need to switch to a completely different technology, looking at different materials and get on a completely different technological path. And I think the foundational technologies, whether it's in engineering, math, device technologies, you name it, we need to have that breadth of technologies and that breadth of disciplines so we can identify these trends and then get on these new trajectories.
You mentioned 1947, the invention of the transistor, that the same year we also invented the cellular concept. And, most people now and the consumers talk about 4G. For them, 5G is the new thing, but you're really focused on 6G, right? Tell us how we're sort of pushing continually, even like 75 years later, still pushing this forward.
Yeah, so indeed, and 6G, we're already on that for more than 5 years and have shown breakthroughs in how we use AI on the air interface, how we combine joint communication and sensing that I mentioned earlier, or more basic, using the massive MIMO technology, another invention at Bell Labs that is now mainstay in 5G, but how we can use that further to enhance capacity from existing cell sites in the 6G era and do that in an energy efficient way. So, and there we collaborate with our colleagues from the mobile network division already in the R&D, but also with our Nokia standards colleagues, because standardization is actually going to start in 6G this year. And then it's not only 6G as in the mobile network, we're also preparing for the next era of optical communication, applying very similar technologies, pushing signal processing to break our own world records on optical fiber. We reached the Shannon limit of optical fiber, but now we're going for, can we do it with lower energy and lower cost? And that means pushing more capacity on a single wavelength using probabilistic constellations shaping, building on our coherent optics. So reducing the number of lasers, hence cost, hence energy consumption. And then go beyond single core. We're already work on getting more capacity through a single fiber with multi-core, coupled multi-core. And also there is crosstalk and all of that. And we're using the insights from MIMO in wireless and apply them there in multi-core fiber.
Well, there's just so many of these things over 100 years that it really wouldn't be a stretch to say that it's hard to imagine the past century without Nokia Bell Labs. And so I guess to wrap this up, I'd want to ask you guys to try to.
I do want to add one more.
Yeah.
Because I've been said you're too hardware focused. Unix. I think we have to say Unix, the mother of all operating systems. It's in Linux, it's in iOS. And this way of thinking, we also apply in our present day research with what we call UNext, future network system, enabling autonomous service generation, really self-evolving network systems using systematically AI, enabling that on this network cloud continuum with distributed decision-making across multiple stakeholders and really symbiotically optimizing that with the application.
So that's how we influenced the last 100 years, the last century, which the world, you could say, technology really defined. I mean, Nokia Bell Labs had a hand in almost every major breakthrough here. Let's look ahead now for the next century. What is your vision? Where do you see it going forward? Anything you can say about? I know sometimes it's hard to predict because who could imagine what happened in the last century, but what's for Nokia Bell Labs the next century?
I think there's lots of different areas. I'll let Peter comment on what he sees. What I'm particularly interested and excited about is what I would call a dynamic digital twin of any physical space. And I briefly touched on that when we talked about the sensing and AI, but being able to capture in real time very complex environments. And digital twins have been around for a long time, but I'm not talking about a digital twin of a single piece of equipment or machinery. I'm talking about digital twins of large complex environments, whether it's an entire factory, an entire airport, an entire city. Why not the world? And then have that in real time. So any change that happens in the physical world, I can immediately capture that. I can immediately analyze it, understand it. So I'm moving from the physical to the digital domain by doing that. And then I can reason on it. I can play what if scenarios. Now there is some change. How do I react to it? I have maybe multiple options. I don't even know what the options are of how I react to it. How do I change something? And what's the best option? So I can play these what if scenarios. I can optimize things in the digital world and then decide how I implement changes back into the physical world. And that can apply to any system. But being able to do that at scale with different levels of granularity, I don't always need to see everything about every little piece of equipment. So I have to be able to sort of zoom in and out on these large systems, and I need to be able to do this in real time. It's not taking a picture, because it's more than a picture. It's really a multimodal, multi-level understanding of the physical world with semantic meaning. It's not just a picture or a point cloud. I know exactly what those objects are I'm seeing. I understand their physical properties. I understand how I can manipulate them. And I want that instantaneously in real time.
Peter, what about you? How do you see the next 10 years, the next 100 years?
Well, I think actually the question next 100 years is maybe easier than the next 10 years. If you would have asked Frank Jewett, what do you see for the next 100 years? He probably would have said the telephone network will not only be used for telephony. It will be used for image. How it would be done and when it would happen, that there would be such things as cathode ray tubes and later on quantum dot LEDs, that he would not predict. But the prediction that we will strive to see each other, that will happen. And I imagine in a similar way, we're still looking at a flat screen here. We're trying to use goggles for 3D. That somewhere in the next century, we will have holographic experience that really feel real. And the word feel is intentionally here, that we may even have tactile contact. It's an ambition. Human nature wants the communication to be as intuitive and as natural as possible. And then the other thing that is also human nature is making our lives easier. Offload us from mundane tasks, whether they're physical tasks, muscle or mental tasks, so that humans are freed up for things that we are good at. That is the creative work, the more complex problem solving, things we enjoy, and then also caring for other people. Would Frank Jewett have predicted that we go for cellular networks on the moon? Maybe not, but I predict that we will go on Mars in the next century.
Well, I hope that we'll have a chance to have this podcast. Maybe next time we can do it as a hologram, or we could, if we stay here long enough. But I'm really appreciate that this was our first episode. Did you want to add something, Thierry?
Peter's right. We will be on Mars sooner than the next 100 years are over. I'm pretty convinced of that.
Well, I could go on and on with both of you. This is really fascinating stuff, but that's it for our first episode. So thankfully, we've got a bunch more episodes to come in which we'll delve into all of this in a far more detail with different guests who will be joining us. In the meantime, thank you to both of you for joining. A special thanks to our producers, Melissa Aiken and Zainab Zakaria. And thank you to everyone who tuned in for this very first episode of A Bit of Tech. For now, please be sure to subscribe, follow, and like us on whatever platform you're getting this podcast, and do stick with us for the rest of the year as we dive into the future throughout the Nokia Bell Labs Centennial Celebration. There's also plenty more to discover on our new and improved website, nokia.com/bell-labs. So until next time, I'm Aron Heller saying thank you for joining us. We'll see you soon on the next episode of A Bit of Tech.